Alright, and welcome to this new video where we discuss things, mathematics or physics on the whiteboard. Now, today what we are going to discuss is something that is always mysterious in quantum mechanics. And essentially we cover kind of both at the same time. On the one hand, we are going to cover uh, why the momentum operator, so here we're going to focus on traditional linear momentum in the x direction, for example, um, is associated to the partial derivative in the with respect to x, okay, and then consequently, and in fact that's what we are starting with. This is connected to the translation operation. So, like an element of a group that translates in space the position vector. Um, so basically, that's what we are going to discuss today, and it shouldn't be too long. Right, okay, so again, to specify the context, what we imagine that we have is that we say that there is a translation operator that we call T with a hat on top. So the hat characterizes an operator acting on a wave function, psi, etc. So I don't specify necessarily all the mathematical aspects. I'm assuming that people have worked at some point, maybe at the end of their high school or later with some wave function, okay, or that you've looked into it on your own. And then you have this particular operator. What it does is that it translates the x here inside to x plus delta x. Now, please keep in mind that depending on whether we deal with a so-called passive or active transformation, we are not going necessarily to go the same way. So here, there's always this discussion of whether or not we should put a plus delta x or a minus delta x, depending on who we want to shift. Whether we want to shift the coordinate system one way, or whether we want to shift the actual curve a certain way as well. So this is not going to give the same, there would be a sign difference here. So here we are assuming that this particular operator is actually adding an extra delta x inside the argument here. Okay? Now, what I'm going to do is fairly straightforward. I'm going to assume that the function psi, and that's only under that condition that this is going to work, is actually infinitely differentiable, with obviously then the derivatives being themselves infinitely differentiable and continuous and so on. Okay, so if this, let's say, acceptable, then what I'm going to do is essentially use the result we've had in the previous video, which was deriving the Taylor series. Okay, and so here I'm simply going to extend the n to infinity in the Taylor series expansion we had found. So I'm going to say that I'm going to use a Taylor series where I take basically that you will need, if you look at the video, you will need to substitute x for the x plus delta x and the x naught for x. Okay, so you would have to make these substitutions for it to work. And what you would find is the following, that f of x plus delta x is equal to the sum for n ranging from 0 to plus infinity, and then you're going to get delta x to the power n divided by n factorial and then f n of x. Okay, so that's what you would get. Now, what I'm going to write, and that's fairly simple, I'm going to write the following. So that's the sum, and then n equals 0 to plus infinity. I'm keeping this delta x delta x to the power n divided by n factorial, and then I've got here d n dxn, and then I'm going to put here f of x. Okay, so then the way I'm going to express that is as follows. I'm going to say that this is sum n from 0 to plus infinity, and then delta x to the power n divided by n factorial, dn dxn, and then this thing here, I keep it as a sort of operator acting on f of x. And so here I can identify this particular object actually as being t of delta x. So that's actually the translation operator, right? Because I've got f of x plus delta x on the left-hand side, and this is equal to that object, f of x. So by definition, that's what the translation operator does. Now, this particular expression, I can say the following. I can say simply formally, just by looking formally and by so-called formal analogy, I can say, but hold on a second. The Taylor expansion of exponential of x is the following, sum. In fact, yeah, exponential of x is sum n ranging from 0 to plus infinity, and then x to the n divided by n factorial. Okay? But here, what I can see is that I've got, if I group together delta x and d over dx, and I put it to the power n, then I could say that this is some sort of x. So consequently, what I get is that the translation operator t delta x can actually be written. Now, in this particular case, I'm going to write it like this, exp, just because otherwise it's a bit, I have to write a bit too small. But that's going to be exp of delta x and then d over dx, whereas the derivative here acts as an operator. So we are taking the exponential of the derivative. Okay, so that's essentially what we're doing. And again, the meaning of this is simply this particular sum. Okay, so that's the actual meaning. The meaning of this particular exponential is simply that. Okay, is this particular sum. Okay, so once we have actually written this particular object, so far the only thing we know is that we have d over dx, which is associated to the translation operator. And in fact, the in the theory of linear representations of groups, and in particular here this is a Lie group, then we've got, I can write it, in fact, here we've got that t of delta x, okay, is a Lie group. In fact, it's a one-dimensional Lie group in that case, is a Lie group with delta x that belongs to the reals. Okay, so delta x belongs to the reals and is a continuous parameter that is going to tell you by how much you are translated. Is a Lie group with delta x and generator. So generator here is a term that is dedicated to the study of Lie groups, and the generator here is d over dx. Okay. So usually the way you get the generator is by taking the derivative of t with respect to its actual single continuous parameter, which is here delta x. And you see that you're going to get d over dx. And in fact, I can say that d over dx is equal, that's by definition, if you will, to d of t d delta x. Okay, so that's the definition of the generator. All right, so that's kind of for the first part. And in fact, then what's going on is that we can say, okay, fair enough. But now, how do we connect that to the momentum? And that's what we are going to see in a minute. Right, okay, so what we want to do at that stage is basically try to find out what is this particular commutator, okay? Because there is a very specific commutator by definition and by construction of the quantum mechanical framework. When you compare, when you look at the commutator between the operator multiplication by x and then the momentum operator. So for now, we don't have the momentum operator, but we have the generator of translations, and we can see what happens when we do that. So we apply it on any psi, assuming it's differentiable and so on. And here is what we are going to get. So we are going to get x d, so sorry, I need to do it slightly differently. So we are going to get x d the dx minus d dx, and then here I need to put the x, and that's applied to psi of x. Okay, so this thing is going to be equal to x d psi dx minus, and here I need to be careful, I've got d of x psi dx. So this is going to be, let's continue on this line for now, x d psi dx minus x d psi dx coming from the product rule, and then I've got minus minus psi, actually. Okay, so what I have in the end is that I've got the following property, that x d dx, the commutator, is equal to minus 1, where the 1 here corresponds to the identity operator. Okay, but then I can say the following. I can say that by construction, but I know that x p is equal to I h bar. Okay, that's something I know. Again, that's an axiom, if you will, of my quantum mechanics. So xp is equal to I h bar, and so consequently, we are getting that p must be equal to minus I h bar d over dx. Okay. Now what that gives us, so that's the first result. And basically I'm now putting back together everything we've seen so far. So let's have a look. So it means as well that d over dx is equal to, so that's minus p divided by I h bar. Okay, and so that's equal to I over h bar p. And so finally, putting everything together, we end up with the following relation, that the translation operation in space is equal to the exponential of I over h bar delta x and then p. Okay, and that's kind of the final result, where p is the linear momentum. And in fact, that's the definition. So this xp is equal to I h bar, that's the definition of the relationship between a particular variable, a so-called generalized coordinate, and its corresponding generalized momentum. Okay, so that's it. I hope you found it helpful, useful, and that it's going to help you remember also these things as well. That's it. If you've got any comments or questions or things you would like I cover as well, please let me know in the comment section, and otherwise we'll see each other in the next video.